Hey there, future tech geniuses. Ready to unlock the secrets of AI? Artificial intelligence, or AI, is like teaching computers to think and learn just like us. From solving puzzles to understanding our voices, AI is everywhere. Think of it as giving a brain to a machine. With AI, robots can help doctors, chatbots can answer our questions, and so much more. The future is bright with AI, and guess what? You're about to be a part of it. Hey there, curious minds. Ever wonder how artificial intelligence is transforming our world? Stick around because today, I'm breaking down how AI is woven into the fabric of our everyday lives and giving you a peek into its technical fundamentals. First up, let's talk about AI in everyday life. Picture this. You wake up, ask Siri for the weather, and get a personalized playlist from Spotify for your morning run. That's AI at work. Virtual assistants like Siri, Alexa, and Google Assistant use natural language processing, or NLP, to understand and respond to your commands. Ever binge-watch Netflix or YouTube? Those smart recommendations? They're powered by AI analyzing your viewing habits. Even your favorite e-commerce sites use chatbots to handle customer service. And let's not forget facial recognition for unlocking your phone or tagging friends on social media. When you use Google Maps or Waze, AI optimizes your route using real-time traffic data. Spam filters in Gmail block phishing attempts, and smart home devices like Nest learn your preferences to keep your home cozy. Personalized ads on Instagram and Facebook? Yep, that's AI too. Now let's dive into the technical side. What exactly is AI? According to Russell and Norvig, AI systems mimic human intelligence to solve problems. There are a few key approaches here. Symbolic AI relies on rule-based logic, like expert systems in medical diagnosis. Connectionist AI uses neural networks to learn patterns. Think image recognition. Evolutionary AI applies genetic algorithms inspired by natural selection, like optimizing robot movements. A major subset of AI is machine learning, or ML. This allows systems to improve with data exposure. Deep learning, a type of ML, uses multi-layered neural networks for tasks like text generation. Reinforcement learning involves algorithms learning by trial and error, like AlphaGo mastering the game of Go. AI isn't one size fits all. We have narrow AI or weak AI, which excels at specific tasks like spam filtering or playing chess. Then there's general AI, a theoretical concept of human-like reasoning across diverse tasks. Not achieved yet, but it's the focus of long-term research. And finally, superintelligent AI, a speculative idea of an AI surpassing human intellect in all domains. This raises many ethical debates about control and safety. Functionality-wise, AI systems are categorized by how they operate. Reactive machines respond to inputs without memory, like IBM's Deep Blue chess computer. Limited memory systems learn from recent data, like self-driving cars. Theory of mind AI, a future concept, would understand human emotions and intentions. And self-aware AI? That's still science fiction. So how does AI work? Core concepts include natural language processing, which lets machines interpret text and speech. Computer vision enables image and video analysis. Think Snapchat filters or medical imaging. And generative AI creates new content, like DALL-E for images or GPT-4 for text. While AI's growth is astonishing, it brings ethical and social considerations. Bias in algorithms can reflect societal prejudices. Data privacy is a big concern with smart devices recording our lives. Job displacement is a reality as automation advances, and accountability is crucial if an AI system causes harm, like in self-driving car accidents. Looking ahead, AI trends include generative AI tools like Midjourney and GitHub Copilot, and breakthroughs in healthcare with AI-driven drug discovery. But we face challenges too, like achieving AGI without unintended consequences and balancing innovation with regulation. In conclusion, AI is reshaping industries in our daily lives. Its potential is vast, but addressing ethical risks and ensuring equitable access are key to making AI a force for good. Thanks for watching.
Hey everyone, today I'm diving into the fascinating evolution of artificial intelligence. Buckle up because we're going on a journey from ancient legends to the cutting-edge reality of AI today. First stop, the early foundations of AI. Long before we had computers, ancient myths like Talos and the Golem hinted at the idea of artificial beings. Thinkers like Aristotle and inventors like Leonardo da Vinci laid down concepts that would inspire future generations. Fast forward to the 17th and 19th centuries and we see mathematicians like Leibniz and George Boole developing symbolic logic. This was crucial for the birth of modern computing. And let's not forget Charles Babbage and Ada Lovelace, who envisioned mechanical computers and the idea of programming. Next, we hit the 1940s and 50s, the birth of modern AI. Alan Turing introduced the Turing machine and the Turing test, concepts that still influence AI today. Then, in 1956, John McCarthy coined the term artificial intelligence at the Dartmouth Conference, marking the official start of AI as a research field. Early programs like Logic Theorist and General Problem Solver emerged, setting the stage for future developments. But it wasn't all smooth sailing. The 1960s to 90s saw both progress and setbacks. Early AI systems focused on symbolic reasoning and expert systems like Mycin. However, they hit a wall with tasks like language processing, leading to the first AI winter due to unmet expectations. The revival came with neural networks. Frank Rosenblatt's perceptron was an early attempt. But it wasn't until the 1980s and the development of backpropagation that machine learning regained momentum. Now let's talk about the rise of machine learning and deep learning from the 2000s to today. The explosion of big data and powerful computers shifted the focus to machine learning. Algorithms like support vector machines outperformed traditional symbolic AI. The real game changer came in 2012, with AlexNet's victory in the ImageNet competition. This breakthrough in deep learning with convolutional neural networks, CNNs, revolutionized the field. Advances in natural language processing, NLP, with models like GPT and BERT have since transformed language understanding and generation. AI is now reshaping industries from healthcare to finance and even autonomous systems. But with great power comes great responsibility. Ethical concerns and bias in AI are critical areas that need addressing. Looking to the future, we distinguish between narrow AI and the dream of artificial general intelligence, AGI. Today's AI excels at narrow tasks, but AGI, which aims to mimic human cognition across various tasks, remains a distant goal. Key trends indicate that future AI will focus on enhancing human-AI collaboration and developing ethical frameworks to ensure AI's benefits are widespread. In conclusion, the history of AI is a roller coaster of ambition, setbacks, and breakthroughs. From ancient myths to modern deep learning, AI continues to evolve, offering new possibilities for our future. Understanding this history is crucial as we navigate its potential and challenges. Thanks for watching, and I'll see you in the next lesson. Hey everyone! Today, we're diving into a fascinating journey through the world of artificial intelligence, or AI, and its evolution to generative AI. Buckle up, because this is going to be an enlightening ride. First, let's break down the difference between AI and augmented intelligence. Artificial intelligence, or AI, refers to systems that operate autonomously. They use algorithms to make decisions without human input. Think of self-driving cars like Tesla Autopilot, which process sensor data to navigate roads on their own. AI shines in efficiency, scalability, and precision, especially in structured tasks. However, it struggles with ambiguous scenarios, such as ethical dilemmas in accidents. On the other hand, augmented intelligence is designed to enhance human decision-making, not replace it. For example, IBM Watson in healthcare analyzes medical scans and flags anomalies, but doctors still finalize the diagnoses. This reduces errors like misdiagnosis in radiology by 30% in some studies, plus it mitigates job displacement by prioritizing human oversight. So why does this distinction matter? A 2022 study found that radiologists using augmented AI tools detected 20% more early-stage cancers than either humans or AI alone. The key takeaway here is that AI excels in automation, while augmented intelligence thrives in collaboration. Now let's trace the technical evolution from traditional AI to generative AI. Starting with traditional AI, these rule-based systems rely on predefined rules. For example, early chatbots like Eliza from the 1960s mimicked conversation using scripted responses. But these systems were brittle and failed with unstructured data like interpreting slang. Next up is machine learning, or ML. This marked a shift where systems learn from data rather than following static rules. We have supervised learning, where labeled data trains models like spam filters. Unsupervised learning finds patterns in raw data like customer segmentation. And reinforcement learning learns via trial and error, as seen in AlphaGo. ML's impact is immense, enabling Netflix's recommendation engine, which drives 80% of its streamed content. Then comes deep learning, or DL. This breakthrough involves neural networks with multiple layers processing unstructured data. An example is convolutional neural networks, CNNs, powering facial recognition in iPhone Face ID. However, DL requires massive datasets, and its black box decision-making raises transparency issues. Finally, we arrive at generative AI. This creates original content like text, images, and code using models like GPT-4 and Stable Diffusion. Applications are vast. DALL-E generates marketing visuals in seconds, and GitHub Copilot suggests code snippets, reducing development time by 55%. But with great power comes great responsibility. Deepfakes can spread misinformation, and copyright disputes arise when artists' styles are used without permission. To wrap up, the distinction between AI and augmented intelligence lies in autonomy versus collaboration, and both have their own unique roles. Generative AI is a double-edged sword, revolutionizing creativity while demanding robust governance like watermarking AI-generated content. This concludes our session on AI versus augmented intelligence. Stay tuned for the next module.
Today we'll cover the core concepts of machine learning and introduce some common algorithms used in the field. This will give you a solid foundation to build upon as you dive deeper into ML. Let's get started. Machine learning, or ML, is a subset of artificial intelligence that enables systems to learn from data and make decisions without being explicitly programmed. Instead of hard-coding rules, we provide data to a machine, and it discovers patterns or learns to make predictions. ML powers technologies like self-driving cars, voice assistants, recommendation systems, and more. It's everywhere. Machine learning can be divided into three broad categories based on how machines learn: supervised learning, unsupervised learning, and reinforcement learning. Let's dive into each one. In supervised learning, we provide the machine with labeled data. That means for each input, we also provide the correct output. The machine's job is to learn the mapping from input to output. Example: predicting house prices based on features like size, location, or number of bedrooms. Common supervised learning algorithms, linear regression, used for predicting continuous values. For example, predicting house prices or stock values. It finds the relationship between input variables, features, and a target output, using a linear equation. Logistic regression, used for binary classification, such as predicting whether an email is spam or not spam. Despite the name, it's a classification algorithm, not regression. Decision trees. A tree-like structure where each node represents a decision based on a feature. It's used for both classification and regression. Example: predicting whether a customer will buy a product based on past behavior. Support vector machines, SVM. SVM finds a boundary, hyperplane, that best separates different classes in the dataset, commonly used for image classification or text classification. In unsupervised learning, the machine works with unlabeled data. It tries to uncover hidden patterns or groupings in the data. There's no correct output provided, and the machine explores the data on its own. Example: grouping customers into segments based on their purchasing behavior or clustering similar products. Common unsupervised learning algorithms. K-means clustering, one of the most popular clustering algorithms. It groups data points into K-clusters based on similarity. Example: segmenting customers into groups based on spending habits. Hierarchical clustering builds a hierarchy of clusters either by merging or splitting them. This creates a tree of clusters that can help understand relationships between data points. Example: grouping species of animals based on genetic similarities. Principal component analysis, PCA. A technique used for dimensionality reduction. PCA transforms high-dimensional data into fewer dimensions while preserving important information. Example: reducing the number of features in a dataset for visualization or speeding up computation. Autoencoders. A type of neural network used for learning efficient data representations in an unsupervised way, often used for anomaly detection or data compression. Example: detecting fraud in financial transactions. Reinforcement learning is a bit different. Here, an agent learns by interacting with an environment. It receives rewards or penalties based on its actions and aims to maximize the total reward. This is often used in dynamic environments like training AI to play games or teaching robots to navigate. Example: a self-driving car receives rewards for following traffic rules and penalties for dangerous behavior. Over time, it learns how to drive safely. Common reinforcement learning algorithms, Q-learning. A type of model-free reinforcement learning algorithm where the agent learns an action value function, also known as the Q function, to find the best action to take in a given state. Example: a robot learns to navigate through a maze by learning which actions yield the highest rewards. Deep Q networks, DQN. An extension of Q-learning that uses deep neural networks to approximate the Q function, enabling it to handle more complex environments. Example: training an AI agent to play video games like Atari, where the state space, game environment, is large. Policy gradient methods. These algorithms directly optimize the agent's policy, which is a probability distribution over actions, by updating it based on the rewards received. Example: used in tasks where real-time decision-making is required, such as controlling a drone. Actor-critic methods. A combination of both policy-based and value-based methods, where the actor suggests actions, and the critic evaluates how good the actions are. Example: used in continuous control tasks like robotic arm manipulation. To wrap up, we've explored the three main types of machine learning: supervised learning, unsupervised learning, and reinforcement learning. We also covered some of the most commonly used algorithms in each type. Machine learning is a vast field, and these algorithms are just the beginning. Stay tuned, and thanks for joining me today. We use language every day. We talk, we write, we read. Language is how we communicate. But did you know that computers can understand language too? This is thanks to natural language processing, or NLP. NLP is a powerful tool that helps computers understand and process human language. It's like teaching a computer to read, write, and speak like us. NLP is used in many applications today, from chatbots to translation apps. It's even used to power virtual assistants like Siri and Alexa. NLP is changing the way we interact with technology. With NLP, we can communicate with computers in a more natural and intuitive way. This video will explore the fascinating world of NLP. We'll learn about its core tasks, algorithms, and real-world applications. Get ready to unlock the magic of language understanding. Natural language processing, or NLP, is a branch of artificial intelligence, or AI. It focuses on enabling computers to understand, interpret, and generate human language. It's about bridging the gap between how humans communicate and how computers process information. The primary goal of NLP is to make it possible for computers to process and analyze large amounts of natural language data. This data can be in the form of text or speech. NLP techniques help computers extract meaning, identify patterns, and even generate human-like text. NLP combines linguistics, computer science, and AI. It uses computational linguistics to analyze the structure and meaning of language. It also leverages machine learning algorithms to learn patterns and make predictions based on language data. NLP is a complex field, but its goal is simple: to enable seamless interaction between humans and computers using natural language. NLP encompasses a wide range of tasks that allow computers to process and analyze human language. Let's explore some of the core NLP tasks. First, text classification. This task involves categorizing text into predefined categories. For example, spam detection classifies emails as spam or not spam. Sentiment analysis determines if a movie review is positive, negative, or neutral. Next, named entity recognition, or NER. NER identifies and classifies named entities in text, such as people, organizations, locations, and dates. For instance, in the sentence "Apple is headquartered in Cupertino," NER would identify Apple as an organization and Cupertino as a location. Then, machine translation. This task focuses on automatically translating text or speech from one language to another. Online translation tools like Google Translate heavily rely on machine translation. Following that, speech recognition. This involves converting spoken language into written text. Virtual assistants like Siri and Alexa use speech recognition to understand our voice commands. Finally, text generation. This task involves generating human-like text, such as writing stories, composing emails, or creating chat responses. Chatbots and virtual assistants utilize text generation to provide natural-sounding responses. These core tasks highlight the diverse capabilities of NLP in understanding and processing human language. NLP algorithms, the brains behind the magic. NLP algorithms are the driving force behind these amazing tasks. Let's delve into some common algorithms used in NLP. First, we have the bag of words, or BO. This simple yet effective algorithm represents text as a collection of words, disregarding grammar and word order. It's often used in text classification tasks. For example, in spam detection, BO can analyze the frequency of words like free or discount to identify spam emails. Next, we have the Hidden Markov Model, or HMM. HMM is a statistical model used for sequential data like text and speech. It's commonly used in speech recognition and part-of-speech tagging. Imagine predicting the next word in a sentence. HMM can help with that. Then, there are recurrent neural networks, or RNNs. RNNs are a type of neural network designed to handle sequential data. They are particularly well-suited for tasks like machine translation and text generation. Think of RNNs as having a memory that allows them to understand the context of words in a sequence. Finally, we have transformers. Transformers are a more recent type of neural network architecture that has revolutionized NLP. They are particularly powerful in capturing long-range dependencies in text, making them ideal for tasks like machine translation and text summarization. These algorithms showcase the complexity and sophistication of NLP in processing and analyzing human language. Real-world applications, NLP in action. NLP is not just a theoretical concept, it has numerous real-world applications that impact our daily lives. First, in customer service, chatbots and virtual assistants powered by NLP are transforming customer service. They can handle customer queries, provide instant support, and personalize interactions. In healthcare, NLP is assisting in medical diagnosis, drug discovery, and patient care. It can analyze medical records, research papers, and patient symptoms to provide valuable insights. In finance, NLP is used in fraud detection, risk assessment, and investment analysis. It can analyze financial news, social media sentiment, and market trends to make informed decisions. In education, NLP is enhancing learning experiences through personalized tutoring, automated grading, and language translation. It can adapt to individual learning styles and provide customized feedback. These are just a few examples of how NLP is being used to solve real-world problems and improve our lives. The future of NLP, a world of possibilities. Natural language processing is revolutionizing the way we interact with technology and the world around us. It enables computers to understand, interpret, and generate human language, bridging the gap between humans and machines. From chatbots to virtual assistants, NLP is transforming industries like customer service, healthcare, finance, and education. As NLP research and development continue to advance, we can expect even more innovative applications in the future. The future of NLP is bright. With its ability to unlock the magic of language understanding, NLP holds immense potential to transform our world and create a future where communication with technology is seamless and intuitive. As we delve deeper into the world of NLP, we unlock a world of possibilities limited only by our imagination. We humans are visual creatures. We rely heavily on our sight. We use our eyes to understand the world around us. But what if machines could see too? This is the fascinating realm of computer vision. Computer vision is a field of artificial intelligence. It enables computers to see and interpret images and videos. Just like our brains process visual information, computer vision algorithms try to understand the content of images and videos. This technology is rapidly changing our world. Computer vision is everywhere. It's in our smartphones, our cars, and even our hospitals. From facial recognition unlocks to self-driving vehicles, computer vision is revolutionizing various industries and aspects of our lives. Imagine a world where computers can diagnose diseases from medical scans, guide robots to perform complex tasks, or even help us create art. This is the promise of computer vision. This field combines concepts from computer science, mathematics, and engineering. It uses complex algorithms to mimic the human visual system. The goal is to enable machines to perceive and interpret visual information just like we do. Think of it as giving computers the gift of sight. This video will explore the key concepts and algorithms that power computer vision. We will delve into the fundamental tasks of computer vision and their practical applications. Join me as we journey into the world of computer vision, a field brimming with potential and transforming our world in unprecedented ways. Computer vision aims to replicate the remarkable capabilities of human vision. To achieve this, computer vision systems are trained to perform several core tasks. Think of these tasks as building blocks. Each building block contributes to a computer's ability to understand and interact with the visual world. First, we have image classification. This is the most basic task. It involves assigning a label to an image based on its content. For example, classifying an image as a cat or a dog. Next, object detection takes a step further. This task involves not only identifying objects in an image but also locating them within the image. Think self-driving cars that need to identify and track pedestrians, other vehicles, and traffic signs. Then there's image segmentation. This task involves dividing an image into meaningful regions or segments. Each segment represents a different object or part of an object. This is crucial for applications like medical imaging, where segmenting a tumor from surrounding tissue can be life-saving. Furthermore, facial recognition, a more specialized task, focuses on identifying individuals based on their facial features. This technology has become ubiquitous in security systems and smartphone authentication. Finally, optical character recognition, or OCR, enables computers to read and interpret text within images. Think of digitizing books or automating data entry from scanned documents. These core tasks form the foundation of computer vision. By mastering these tasks, computer vision systems can tackle a wide range of real-world problems. Imagine showing a computer an image of a sunflower. How does it know it's looking at a sunflower and not a rose or a daisy? This is where image classification comes in. It's the task of teaching computers to recognize and categorize images. It's like giving a computer a visual dictionary and teaching it to match pictures to words. One of the most revolutionary algorithms in image classification is the convolutional neural network, or CNN. CNNs are designed to process pixel data efficiently. They use specialized layers to learn hierarchical representations of images, from simple edges and textures to complex shapes and patterns. ResNet, short for residual network, is a specific type of CNN that introduced the concept of skip connections. These connections help to address the vanishing gradient problem, allowing for the training of much deeper networks. Deeper networks can learn more complex features, leading to improved accuracy in image classification. For applications on devices with limited computational power like smartphones, MobileNet comes into play. MobileNets are lightweight CNNs designed for speed and efficiency. They achieve this through depth-wise separable convolutions, which reduce the number of computations significantly. These powerful algorithms have propelled image classification to new heights. From identifying objects in our photos to assisting in medical diagnoses, image classification is transforming numerous fields. Object detection, locating the where. While image classification tells us what is in an image, object detection goes a step further by revealing where those objects are located. Think of it as giving computers the ability to see and understand the world like we do. One of the groundbreaking algorithms in object detection is YOLO, or you only look once. True to its name, YOLO processes images in a single pass, making it incredibly fast. It divides the image into a grid, and predicts bounding boxes and class probabilities for objects within each grid cell. RCNN, or Region-Based Convolutional Neural Network, takes a different approach. It first identifies potential regions of interest in an image where objects might be present, and then it uses a CNN to classify the objects within those regions. RCNN and its variants, like Fast RCNN and Faster RCNN, have significantly improved the accuracy of object detection. SSD, or Single-Shot Multi-Box Detector, combines aspects of both YOLO and RCNN. It's known for its speed and accuracy, making it suitable for real-time applications like video surveillance. Object detection is crucial for a wide array of applications. From self-driving cars that need to identify pedestrians and other vehicles to robots that navigate complex environments, object detection is making our world safer and more efficient. Section 5. Beyond the basics, image segmentation, facial recognition, and OCR. As we delve deeper into the realm of computer vision, we encounter more specialized tasks that build upon the foundations of image classification and object detection. These tasks further enhance a computer's ability to comprehend and interact with the visual world. Image segmentation, for instance, goes beyond simply identifying objects. It provides a pixel-level understanding of images, outlining the boundaries of each object. This is crucial for medical imaging, where precise segmentation of organs and tissues is vital for diagnosis and treatment planning. Algorithms like UNet, FCN, or fully convolutional network, and mask RCNN have revolutionized image segmentation, enabling remarkable precision in various fields. Facial recognition focuses on a specific type of object, human faces. This technology has become ubiquitous in security systems, smartphone authentication, and even social media. Algorithms like eigenfaces, FaceNet, and MTCNN, or multitask cascaded convolutional network, have driven advancements in facial recognition accuracy and efficiency. Optical character recognition, or OCR, bridges the gap between the visual and textual worlds. It enables computers to read and interpret text within images, converting scanned documents, handwritten notes, or even text embedded in natural scenes into editable digital text. Algorithms like Tesseract, CRNN, or convolutional recurrent neural network, and deep learning-based OCR models have made significant strides in OCR accuracy, particularly for challenging handwriting styles and complex layouts. These advanced tasks showcase the incredible versatility and power of computer vision. From healthcare to security to human-computer interaction, these technologies are shaping the future of numerous industries. Computer vision's expanding horizon. As we stand at the cusp of a new era driven by artificial intelligence, computer vision is poised to play an even more transformative role in our lives. The field is rapidly evolving, fueled by breakthroughs in algorithms, computing power, and the availability of massive data sets. The future of computer vision is brimming with possibilities. Imagine a world where augmented reality seamlessly blends with our physical surroundings, providing us with real-time information and enhanced experiences. Envision healthcare systems where computer vision aids in early disease detection and personalized treatment plans. Picture smart cities that leverage computer vision to optimize traffic flow, enhance public safety, and minimize environmental impact. However, as with any powerful technology, ethical considerations must guide the development and deployment of computer vision. Privacy concerns, bias in algorithms, and the potential for misuse are crucial issues that demand careful attention. As we venture further into the realm of computer vision, let us proceed with both excitement and responsibility. By harnessing the power of this transformative technology ethically and thoughtfully, we can unlock its full potential to benefit humanity and create a brighter future for all. Robots are no longer just a figment of science fiction. They are here, in our factories, our homes, and even exploring Mars. But how do these machines actually work? What makes them tick? Let's uncover the magic behind robots. Imagine a world where robots assist us in our daily lives. They could clean our homes, cook our meals, and even drive our cars. In manufacturing, robots perform repetitive tasks with precision. In healthcare, robotic surgery is becoming increasingly common, allowing for minimally invasive procedures and faster recovery times. As technology advances, we can expect even more incredible innovations in the years to come. Robotics is a fascinating field that combines multiple disciplines. It's like a melting pot of science, engineering, and computer science. At its core, robotics is all about creating machines that can perform tasks autonomously or semi-autonomously. Think of a robot as a puzzle with many interlocking pieces. We have mechanical engineering, which deals with the design and construction of the robot's physical body. Then there's electrical engineering, responsible for the robot's power systems and electronic components, and let's not forget computer science, the brains behind the operation. Robotics is a true testament to the power of interdisciplinary collaboration. To understand how robots work, we need to grasp three fundamental concepts: perception, planning, and control. These three pillars form the foundation of robotics. Perception allows a robot to sense and interpret its surroundings, much like we do with our senses. It's about collecting information from the environment using sensors. Planning is like a robot's internal GPS, enabling it to figure out the best way to achieve a given task. Think of it as the robot's ability to map out a route, avoiding obstacles and choosing the most efficient path. Finally, control ensures that the robot executes the planned actions smoothly and accurately. This involves coordinating the robot's movements and making sure it interacts with its environment safely and effectively. Section 4. Robots that perceive unveiling the world around them. Imagine a robot navigating a busy street. To avoid collisions, it needs to perceive its surroundings accurately. Robots use a variety of algorithms to make sense of the vast amount of sensory data they collect. One such algorithm is called SLAM, which stands for Simultaneous Localization and Mapping. SLAM allows a robot to build a map of its environment while simultaneously keeping track of its own location within that map. Another important algorithm is the Kalman filter, a powerful tool for estimating the state of a system from noisy sensor measurements. Computer vision is another crucial aspect of robot perception, enabling robots to see and interpret images and videos. This allows them to recognize objects, track movements, and even understand human gestures. Section 5. Robots that plan, navigating the maze of possibilities. Now that our robot can perceive its environment, it needs to figure out how to move around. This is where planning algorithms take center stage. These algorithms help robots find the best way to get from point A to point B, taking into account obstacles, dynamics, and other constraints. One widely used planning algorithm is A*, pronounced A*, guiding it through a complex environment. It finds the shortest path between 2 points, considering factors like distance, terrain, and energy consumption. For more complex scenarios, we have algorithms like rapidly exploring random trees, RRT, and probabilistic roadmaps, PRM. These algorithms are particularly useful for robots operating in high-dimensional spaces or environments with dynamic obstacles. Section 6. Robots in motion, the art of control and coordination. With a plan in place, our robot is ready to put its actuators into action. This is where control algorithms come into play, ensuring that the robot's movements are precise, stable, and efficient. One of the most fundamental control algorithms is the proportional integral derivative, PID, controller. PID controllers are used extensively in robotics to regulate speed, position, and other variables. For more sophisticated control tasks, we have Model Predictive Control, MPC, which takes into account the robot's dynamics and future predictions to optimize its behavior. Inverse kinematics is another essential tool, allowing us to determine the joint angles of a robot arm to achieve a desired end effector position. This is crucial for tasks like grasping, manipulation, and precise positioning. Am I the only one who's amazed by how robots never get lost? Let's dive into their secret. Alright, let's talk about how robots figure out their location. It's all about localization and mapping. Imagine you're in a new city without GPS. How do you find your way? Well, robots face the same challenge and use some cool algorithms to solve it. First up, Monte Carlo localization, or MCL. Think of it like throwing a bunch of confetti and seeing where each piece lands. Each piece represents a possible location of the robot. As the robot moves, it updates these guesses to zero in on its true position. This is how your robotic vacuum navigates your home without getting stuck. Next, we have the Extended Kalman filter, or EKF. Picture it like blending ingredients in a smoothie. EKF mixes data from different sensors like GPS, cameras, and LiDAR to estimate the robot's position more accurately. This method is key for self-driving cars. Lastly, occupancy grid mapping. Imagine a blank grid as the environment. The robot marks each cell as occupied or free, creating a map it can use for navigation. This is how indoor robots create floor plans and avoid obstacles. So the next time you see a robot cruising along, you'll know the tech behind it. This is going to blow your mind. The cosmos of artificial intelligence is vast and ever-expanding. Within this fascinating realm, expert systems stand as pioneers, early explorers venturing into the simulation of human expertise. Imagine a computer program capable of diagnosing diseases like a seasoned doctor. Picture a system offering financial advice with the acumen of a Wall Street veteran. These are not futuristic fantasies, but the very real capabilities of expert systems. Expert systems represent a significant stride towards artificial intelligence. They are designed to replicate the decision-making processes of human experts. By capturing and utilizing vast stores of knowledge, these systems empower us to solve complex problems, automate intricate tasks, and even gain new insights from mountains of data. You need to watch this if you struggle with understanding AI. At their core, expert systems are sophisticated computer programs. But these are not your everyday applications. They distinguish themselves by their unique ability to emulate the reasoning and problem-solving skills of human experts within specific domains. Imagine a master chess player, strategizing moves with remarkable foresight. Expert systems operate on a similar principle, employing a wealth of specialized knowledge to analyze situations and make informed decisions. Their primary goal is to tackle real-world problems that would typically require human intelligence and experience. Consider a medical diagnosis expert system. This digital physician would be equipped with a vast database of medical knowledge, symptoms, and treatment protocols. By analyzing a patient's symptoms and medical history, the system can provide potential diagnoses, suggest further tests, and even recommend treatment plans. You need to hear this if you're fascinated by artificial intelligence. The power of expert systems lies in their unique architecture, a synergy of two fundamental components, the knowledge base and the inference engine. Think of the knowledge base as the system's vast library. This is where all the domain-specific knowledge painstakingly gathered from human experts is stored. Just like a well-organized library, the knowledge base is meticulously structured for efficient retrieval. It contains facts, rules, heuristics, and other nuggets of wisdom that the system needs to draw upon. Now imagine a skilled librarian who knows exactly where to find the right book for any inquiry. That's the role of the inference engine. The inference engine is the brainpower behind the operation. It accesses the knowledge base, applies logical rules and reasoning, and ultimately delivers insightful conclusions or recommendations. This dynamic duo, the knowledge base and the inference engine, work in tandem, transforming raw data into actionable intelligence. I bet you didn't know that knowledge within an expert system takes on two primary forms, declarative and procedural. Declarative knowledge forms the foundation, encompassing facts, concepts, and relationships within the domain. Think of it as the what of the knowledge base. For instance, in a medical expert system, declarative knowledge would include statements like, high fever is a symptom of infection, or diabetes increases the risk of heart disease. Procedural knowledge, on the other hand, outlines the how, the steps, strategies, and procedures employed by experts to solve problems. In the medical context, procedural knowledge might describe the steps involved in diagnosing a particular illness, or the protocol for treating a specific condition. This dynamic interplay between declarative and procedural knowledge empowers expert systems to not only understand the domain, but also to mimic the decision-making processes of human experts. Forward and backward chaining. You need to hear this if you're a problem solver. Imagine yourself solving a maze. You can start at the entrance and systematically explore each path until you reach the exit. That's forward chaining. Alternatively, you could start at the exit and work your way backward, retracing the steps that lead to the entrance. That's backward chaining. Expert systems employ similar reasoning strategies. Forward chaining starts with the available data and uses rules to deduce new information, ultimately reaching a conclusion or goal. It's like a detective piecing together clues to solve a case. Backward chaining, however, begins with a hypothesis or goal and works backward through the rules to see if the available evidence supports it. Consider a simple example: diagnosing a car problem. Forward chaining would involve observing symptoms like engine sputtering and difficulty starting, then applying rules to deduce a faulty fuel pump. Backward chaining would start with the hypothesis of a faulty fuel pump, and then check if the car exhibits corresponding symptoms. I bet you didn't know there are different types of expert systems. Welcome to Section 6, Types of Expert Systems. Expert systems, much like human experts, come in various flavors, each specializing in different approaches to knowledge representation and reasoning. Three prominent types stand out: rule-based systems, model-based systems, and fuzzy logic systems. Rule-based systems, as their name suggests, rely on a set of predefined rules to represent knowledge and guide decision-making. These rules, often expressed in an if-then format, capture the heuristics and experience of human experts. For instance, a rule in a financial expert system might be, if the debt-to-equity ratio is high, then consider refinancing options. Model-based systems, on the other hand, employ models to simulate the behavior of complex systems. These models can range from simple equations to sophisticated simulations, capturing the underlying principles governing the domain. Think of an expert system designed to predict weather patterns. Fuzzy logic systems excel in handling uncertainty and imprecision, mimicking the human ability to reason with vague or incomplete information. Unlike traditional logic, which operates on absolute true or false values, fuzzy logic introduces degrees of truth, allowing for more nuanced and human-like decision-making. A medical expert system using fuzzy logic could, for example, consider a range of symptoms and their severity to arrive at a diagnosis. I bet you didn't know how expert systems are transforming various industries. In the realm of medical diagnosis, Mycin, a pioneering expert system developed in the 1970s, showcased the power of rule-based reasoning. Mycin excelled in diagnosing bacterial infections, leveraging a vast knowledge base of medical rules and patient data. Financial analysis, too, has been revolutionized by expert systems. Systems like Protos, employing a combination of rule-based and case-based reasoning, assist financial analysts in making investment recommendations, evaluating loan applications, and detecting fraudulent transactions. But the story doesn't end there. Expert systems have ventured into the legal domain, where systems like LDS, legal decision support, aid lawyers in legal research, case analysis, and even predicting court decisions. Underpinning these impressive applications are sophisticated algorithms. The Rete algorithm, for instance, efficiently processes vast rule sets in real time, making it a cornerstone of many rule-based expert systems. Bayesian networks, on the other hand, excel in handling uncertainty, making them invaluable in domains like medical diagnosis and risk assessment. Applications of expert systems. The impact of expert systems extends far beyond these specific examples, permeating countless industries and aspects of our lives. In manufacturing, expert systems optimize production processes, ensuring efficiency and quality control. In customer service, they power intelligent chatbots, providing instant support and personalized experiences. The world of education benefits from expert systems that personalize learning pathways, tailoring educational content to individual student needs. As we venture further into the age of information, expert systems stand as testaments to our ingenuity. They empower us to harness the power of artificial intelligence, not to replace human expertise, but to augment it, amplify it, and make it accessible to all. Expert systems represent a profound shift in our relationship with technology, a step towards a future where human knowledge and machine intelligence collaborate to solve our most pressing challenges and unlock a world of possibilities. I don't think people understand how powerful reinforcement learning is. Today I'm diving into the fascinating world of reinforcement learning, or RL. If you're curious about how machines learn to make decisions on their own, you're in the right place. From robots to video games and self-driving cars, RL is paving the way for some of the most exciting advancements in artificial intelligence. Reinforcement learning is a type of machine learning where an agent learns to make decisions by taking actions in an environment to maximize a cumulative reward over time. Unlike supervised learning, where the model is trained on labeled data, RL involves learning from experience through trial and error. So let's break down the key elements of RL. First, we have the agent, the learner or decision maker. Then there's the environment, everything the agent interacts with. The state is the current situation of the agent within this environment. Actions are the choices the agent can make, and rewards are the feedback the agent receives after taking an action. The policy is the strategy the agent uses to decide its actions. And finally, the value function, a measure of the long-term benefit of states and actions. The RL process revolves around the interaction between the agent and the environment. The agent starts in a particular state, takes an action, and receives feedback in the form of a reward. The goal of the agent is to learn a policy that tells it what actions to take to maximize its long-term reward. There are two main types of reinforcement learning, model-based and model-free. In model-based RL, the agent learns a model of the environment and uses that model to plan actions. Imagine a robot building a map of its surroundings and using that to navigate. In model-free RL, the agent learns directly from experience without building a model of the environment. For example, a robot learning to walk without explicitly modeling the physical world. One of the key challenges in reinforcement learning is balancing exploration and exploitation. Exploration means trying new actions to discover better strategies, and exploitation means using known actions that yield the highest reward. Finding the right balance between these two is crucial for an RL agent to perform optimally. Now let's explore some of the most commonly used algorithms in reinforcement learning. Q-learning is one of the most popular model-free RL algorithms. It seeks to learn the Q-value, quality, of each action in a state. This represents the expected cumulative reward from taking that action and following the optimal policy thereafter. SARSA is another model-free algorithm similar to Q-learning, but with a slight difference. It updates the Q value based on the action that the agent actually takes, not the maximum possible action. This makes SARSA a more conservative approach. Deep Q networks or DQNs extend Q learning by using neural networks to approximate the Q values for each action in a given state. This approach is scalable to large or continuous state spaces, making it ideal for applications like video games and robotics. Policy gradient methods directly learn the policy that maximizes the expected reward, instead of learning the Q values. This is especially useful in environments with continuous action spaces, such as robotic control. Actor-critic algorithms combine the benefits of value-based methods and policy-based methods. The agent has two components: the actor, which learns the policy, and the critic, which evaluates the action taken by the actor by learning the value function. Monte Carlo methods estimate the expected reward by running complete episodes and using the total return to improve the policy. This method is useful for improving strategy over several runs, like in board games such as Go or chess. Reinforcement learning has a wide range of real-world applications. In robotics, RL is used to teach robots how to perform complex tasks, such as walking, grabbing objects, or navigating through obstacles. Autonomous vehicles use RL to learn to navigate in traffic, avoid obstacles, and follow road rules. In gaming, RL has been instrumental in developing agents that can outperform human players. In finance, RL is used in trading systems to learn optimal investment strategies. And in healthcare, RL optimizes treatment plans and manages resources in hospitals. So, there you have it. We've explored the fundamentals of reinforcement learning, from the RL process to common algorithms and their application. Welcome to this video on fuzzy logic. Fuzzy logic is a powerful tool for dealing with uncertainty and imprecise information. Unlike traditional logic that deals strictly with true or false values, fuzzy logic allows for reasoning in degrees of truth, making it incredibly useful for complex real-world applications like control systems, decision-making, and pattern recognition. In this video, we'll explore the basics of fuzzy logic and dive into some of the most common algorithms. Let's get started. Fuzzy logic is a mathematical framework for reasoning that resembles human decision-making. It allows for approximate reasoning, which means rather than relying on strict binary values like true or false, it uses degrees of truth between 0 and 1. Imagine describing how hot it is outside. Instead of saying it's either hot or not hot, fuzzy logic allows for descriptions like slightly hot or very hot by assigning degrees to these terms. Before we dive deeper, let's look at some of the key concepts in fuzzy logic. A fuzzy set is a set where each element has a degree of membership ranging between 0 and 1. In traditional set theory, an element either belongs to a set or it doesn't. Membership is either 0 or 1. In fuzzy logic, an element can partially belong to a set. For example, the fuzzy set hot temperatures could assign a degree of membership to a temperature of 80 degrees Fahrenheit, saying it's 0.7 hot, meaning it's somewhat hot, but not extremely. A membership function defines how each input value is mapped to a membership degree in a fuzzy set. It's a curve that determines the degree of truth for each element. Common membership functions include triangular, trapezoidal, and Gaussian. For example, in a temperature control system, a membership function might describe how hot a given temperature is, where 60 degrees Fahrenheit has a low membership, 80 degrees has a medium membership, and 100 degrees has a high membership. Linguistic variables are variables whose values are words or sentences rather than numbers. For example, in a fuzzy logic system for air conditioning, the linguistic variable temperature might have values like cold, warm, or hot. These linguistic variables are described by fuzzy sets. As another example, the variable speed in a car's cruise control system could have linguistic values like slow, moderate, and fast. A fuzzy logic system generally consists of 4 main components. Let's walk through each of them. Fuzzification is the process of converting crisp, precise inputs into fuzzy values using membership functions. It allows real-world data to be interpreted by the fuzzy logic system. For example, if the input temperature is 75 degrees Fahrenheit, fuzzification might map it as 0.4 cold and 0.6 warm based on predefined membership functions. Once inputs are fuzzified, the system applies fuzzy inference to make decisions. Inference involves applying if-then rules which use fuzzy logic to determine the degree of truth of different possible actions. An example of a fuzzy rule would be, if temperature is cold, then increase heater. If temperature is warm, then keep the heater stable. Fuzzy inference methods include Mamdani inference and Sugino inference. We'll discuss these methods in detail soon. The rule base contains a collection of if-then rules that form the logic of the fuzzy system. These rules define how different fuzzy variables interact and dictate the system's behavior. For example, in a washing machine, the rule base could include rules like, if clothes are very dirty, then set washing time to long. If clothes are slightly dirty, then set washing time to short. After fuzzy inference, the output is still a fuzzy value. Defuzzification converts this fuzzy output back into a crisp value that can be used in the real world. The most common defuzzification method is the centroid method, which finds the center of the area under the curve of the fuzzy output. For example, in a fuzzy temperature control system, defuzzification might convert a fuzzy value of somewhat cool into a specific temperature setting like 68 degrees Fahrenheit. Now that we've covered the basics of fuzzy logic, let's explore some of the most common algorithms and methods used in fuzzy logic systems. The Mamdani fuzzy inference system is the most widely used fuzzy inference approach. It is especially popular in control systems. How it works: it uses fuzzy sets for both inputs and outputs. Fuzzy rules are applied to map inputs to fuzzy outputs. The final output is obtained by defuzzifying the aggregated fuzzy output. Example: a fuzzy logic thermostat may use Mamdani inference to determine whether to increase, decrease, or maintain the temperature based on fuzzy inputs like somewhat cold or very hot. The Sugino fuzzy inference system is similar to Mamdani, but with one key difference. The output of each rule is a crisp function rather than a fuzzy set. How it works: instead of fuzzy output sets, Sugino uses a linear or constant function to compute the output. This is especially useful when you need a precise output, such as in control systems where you need exact values for control. Example: a water flow control system might use a Sugino model to calculate the exact amount of water to release based on fuzzy inputs like slightly full or very full. Fuzzy C-means is a clustering algorithm that allows one data point to belong to multiple clusters with different degrees of membership. How it works: data points are assigned a membership degree to each cluster center. The algorithm iteratively updates the cluster centers and membership values to minimize the distance between data points and cluster centers. Example: in image processing, fuzzy C-means can be used to cluster pixels into groups like partly edge and partly background, which helps in edge detection and image segmentation. Fuzzy logic has a wide range of applications across various industries due to its ability to handle imprecision and uncertainty. Let's take a look at some key areas where fuzzy logic is commonly used. 1. Control systems. Fuzzy logic is used in control systems for applications like washing machines, air conditioners, and even autonomous vehicles. Example: a fuzzy controller in a washing machine can adjust the wash cycle based on how dirty the clothes are. 2. Robotics. Fuzzy logic is often used in robotics for path planning, obstacle avoidance, and navigation. Example: a robot vacuum cleaner uses fuzzy logic to decide whether to slow down, speed up, or turn based on the proximity of obstacles. 3. Medical systems. In medical diagnosis, fuzzy logic helps handle imprecise symptoms and complex diagnostic rules. Example: a fuzzy system might assess symptoms like slightly elevated temperature or moderate headache to diagnose an illness. 4. Consumer electronics. Fuzzy logic is embedded in many consumer electronics for improved user experience. Example: cameras use fuzzy logic for autofocus, determining the sharpness of an image based on fuzzy rules. Our brains are amazing. They process information with billions of interconnected neurons. This biological marvel inspired a powerful tool in artificial intelligence neural networks. Neural networks are a type of machine learning algorithm. They learn from data, just like our brains do. Neural networks drive many technologies we use today, including facial recognition software and virtual assistants. These networks are revolutionizing fields like medicine, finance, and transportation. Neural networks are the foundation for many future AI advancements. They hold the key to solving complex problems that have long eluded traditional computing methods. Let's delve deeper into the fascinating world of neural networks. Imagine a neural network as a factory. The factory takes raw materials and processes them into a finished product. In a neural network, the raw materials are the input data. The finished product is the output or prediction. The factory has different layers, each performing a specific task. A neural network also has layers, an input layer, hidden layers, and an output layer. The input layer receives the data. The hidden layers process the data. And finally, the output layer produces the result. Think of each layer as a group of workers. Each worker receives information, processes it, and passes it on. The connections between these workers are crucial. They determine how information flows through the network. Each worker in our factory is an artificial neuron. These neurons are modeled after the neurons in our brains. Each neuron receives input signals. These signals could be pixel values in an image or the price of a stock. Each input signal is multiplied by a weight. A weight represents the strength or importance of that connection. A higher weight means the input is more important for the neuron's decision. After weighting the inputs, the neuron adds them up. Then it adds a bias term. This bias helps the neuron make better decisions. Think of it as the neuron's personal preference. Finally, the neuron applies an activation function. This function determines how active the neuron will be. It decides whether the neuron should fire and pass on a strong signal or stay quiet. Just like there are different types of factories, there are different types of neural networks. Each type is designed for a specific purpose. Feed-forward neural networks, FNNs, are the simplest type. Data flows in one direction, from input to output. They are used for tasks like predicting house prices or classifying images. Convolutional neural networks, CNNs, are designed for image recognition. They use filters to detect patterns and features in images. CNNs power facial recognition software and self-driving cars. Recurrent neural networks, RNs, are good at processing sequences of data. They have a memory that allows them to remember past information. RNs are used in natural language processing, speech recognition, and machine translation. Training neural networks, a learning process. How do neural networks learn? Through a process called training. Think of training as teaching a dog new tricks. We give the dog commands and it learns from feedback. In neural network training, we feed the network with labeled data. This data includes the input and the desired output. For example, we might feed the network images of cats and dogs, labeled with the correct animal. The network makes predictions on this data. We compare the predictions to the actual labels. The difference between them is called the loss. Our goal is to minimize this loss. We use a technique called backpropagation. This process adjusts the weights and biases of the neurons to reduce the loss. It's like correcting the dog when it makes a mistake. We repeat this process many times. The network learns from its mistakes and gets better at making predictions. Overfitting and underfitting, challenges in training. Training a neural network can be tricky. Sometimes the network becomes too specialized in the training data. This is called overfitting. It's like the dog learning a trick too well. It can only perform it in the exact same way it was trained. Overfitting leads to poor performance on new unseen data. To prevent overfitting, we use techniques like dropout and regularization. These techniques help the network generalize better. On the other hand, if the network is too simple, it might not learn the complexities of the data. This is called underfitting. It's like the dog not understanding the trick at all. Finding the right balance between overfitting and underfitting is crucial for good performance. Deep learning, unlocking complexity. Imagine a neural network with many hidden layers. This is called a deep neural network. Deep learning is all about using these powerful networks to solve complex problems. With each additional layer, the network can learn more abstract representations of the data. It's like adding more layers of understanding to the dog's brain. Deep learning has revolutionized many fields. It has led to breakthroughs in image recognition, natural language processing, and drug discovery. Real-world applications from vision to diagnosis. Neural networks are being used in countless applications today. In self-driving cars, neural networks process data from cameras and sensors. They identify objects, make decisions, and navigate the roads. In healthcare, neural networks can analyze medical images to detect diseases like cancer. They can also predict patient outcomes and personalized treatment plans. These are just a few examples of how neural networks are transforming our world. The possibilities are endless. Challenges and future directions. Despite their remarkable capabilities, neural networks still face challenges. One challenge is the need for large amounts of labeled data. Collecting and labeling this data can be time-consuming and expensive. Another challenge is the black box problem. It's often difficult to understand how neural networks make decisions. This lack of transparency raises ethical concerns, especially in sensitive applications like healthcare and finance. Researchers are constantly working to improve neural networks. They are exploring new architectures, training algorithms, and ways to make these networks more interpretable. Conclusion: neural networks and the future of AI. Neural networks are powerful tools that are revolutionizing artificial intelligence. They learn from data, make predictions, and are transforming countless industries. While challenges remain, the future of neural networks is bright. As research progresses, we can expect even more innovative applications that will shape our future. Neural networks are a testament to the power of human ingenuity. By mimicking the human brain, we are creating machines that can solve some of the world's most pressing problems. The journey of neural networks has just begun.
Welcome to this video on evolutionary computation. Evolutionary computation is a subfield of artificial intelligence that mimics the process of natural evolution to solve optimization problems. It's a powerful method for finding solutions to complex tasks where traditional techniques may fall short. In this video, we'll explore the key concepts behind evolutionary computation and walk through some of the most common algorithms, including genetic algorithms, evolution strategies, and more. Let's begin. Evolutionary computation is a family of algorithms inspired by the mechanisms of biological evolution, such as reproduction, mutation, recombination, and selection. These algorithms are used to find optimal or near-optimal solutions in complex search spaces. The core idea is to evolve a population of candidate solutions over several generations, gradually improving their quality using principles from natural selection. Let's break down the fundamental concepts of evolutionary computation that serve as the building blocks for all evolutionary algorithms. The population in evolutionary computation is a group of potential solutions to the problem. Each individual in the population represents a candidate solution, often encoded as a string or array of values, similar to chromosomes in biology. For example, in an optimization problem for designing an efficient antenna, each individual in the population could represent a different antenna configuration. The fitness function is a key component in evolutionary computation. It evaluates how good or fit each individual is at solving the problem. The higher the fitness, the better the solution. How it works. The fitness function assigns a numerical score to each individual based on how well it performs the desired task. The best individuals are more likely to pass on their traits to the next generation. Example: in a traveling salesman problem, the fitness function might calculate the total distance traveled, with shorter distances resulting in higher fitness scores. Selection is the process by which individuals are chosen to pass on their genes to the next generation. The fittest individuals have a higher chance of being selected, but diversity is maintained by allowing less fit individuals to also contribute occasionally. Example: in a robot path planning problem, the best robot paths, those that avoid obstacles and minimize travel time, are selected for reproduction in the next generation. Reproduction, also called crossover, is the process of combining two parent solutions to produce new offspring. This mimics the biological process where offspring inherit traits from both parents. How it works. The crossover operation takes portions of the two parent solutions and combines them to form a new solution, hoping to inherit the best traits from both. Example: in a problem of evolving neural network architectures, crossover could combine the hidden layer structure of one parent with the activation functions of another. Mutation introduces small random changes to individuals in the population, helping to maintain genetic diversity and explore new areas of the search space. How it works. Mutation randomly alters one or more genes in an individual. For example, if an individual represents a sequence of numbers, mutation might change one number in the sequence. Example, in an optimization problem for aircraft design, a mutation could randomly change a wing angle or engine power level to explore new configurations. A generation is a complete cycle of selection, reproduction, mutation, and fitness evaluation. After several generations, the population evolves toward better solutions. How it works. At the end of each generation, the new population is evaluated and the process is repeated for a predefined number of generations or until a satisfactory solution is found. Example, in a resource allocation problem, after many generations, the population might evolve to near-optimal solutions for distributing resources efficiently. Now, let's explore some of the most common evolutionary algorithms that implement these concepts. A genetic algorithm, or GA, is the most widely known evolutionary algorithm. It models the process of natural selection, where the fittest individuals are selected for reproduction to produce offspring for the next generation. So, how does it work? GAS begin with a randomly generated population. In each generation, individuals are selected based on their fitness, crossover and mutation are applied, and the process is repeated. For example, JAS are used for job scheduling, route optimization, and financial portfolio optimization. Evolution strategies, or ES, focus more on mutation and less on crossover compared to genetic algorithms. These algorithms use real-valued parameters to mutate individuals and rely heavily on the selection process to guide evolution. Here's how it works. ES maintains a population of candidate solutions, applies mutations to create offspring, and selects the best individuals for the next generation based on fitness. For instance, evolution strategies are commonly used in continuous optimization problems, such as designing control systems for robots or tuning hyperparameters in machine learning models. Genetic programming, or GP, is an extension of genetic algorithms where the individuals in the population are not simple strings, but computer programs. GP evolves programs to perform a specific task, optimizing them over generations. So how does it work? GP creates a population of programs, applies selection and mutation, and produces new generations of programs that perform the task better. For example, GP can be used to automatically generate algorithms for tasks like symbolic regression, robot control, and automated trading strategies. Differential evolution, or DE, is an evolutionary algorithm designed for optimizing real-valued functions. It uses a simple but effective mutation scheme to explore the search space. How it works. DE creates new individuals by adding a weighted difference between two population members to a third member, creating a candidate solution that is evaluated and possibly replaces the original. For example, Delaware is often used in engineering design, signal processing, and neural network training. Evolutionary algorithms have a wide range of applications in many fields. Here are just a few examples. Evolutionary computation is frequently used to solve complex optimization problems that are difficult for traditional algorithms. This includes engineering design optimization, where we find the best parameters for complex systems like aircraft, bridges, and chemical processes. It also covers logistics and route planning, optimizing routes for delivery vehicles or public transportation. Evolutionary algorithms can also be used to optimize machine learning models, including the architecture of neural networks and hyperparameters. For example, neuroevolution combines evolutionary algorithms with neural networks to automatically design and evolve deep learning models. Evolutionary algorithms are also used in game development to create AI opponents that evolve and adapt to different playing styles. In evolutionary game theory, evolutionary strategies are used to optimize the behavior of AI agents, making them more competitive. Evolutionary computation is a fascinating and versatile approach to solving complex problems. By mimicking natural evolution, we can evolve solutions to problems that are otherwise difficult to tackle with traditional methods. Whether you're optimizing a mechanical system, developing a machine learning model, or solving a game strategy, evolutionary algorithms provide a powerful toolset. Thanks for watching and stay tuned. Welcome to this section on knowledge representation and reasoning, or KR for short. KR is a core area of AI that deals with how information is structured so AI systems can reason, make decisions, and solve problems. Let's dive in. KR refers to encoding information in a way that AI systems can process effectively. It's not just about data storage, but organizing it to enable reasoning. Key approaches include logic-based representation. Uses formal logic to describe facts and rules about the world, for example, propositional and predicate logic. Semantic networks. Use nodes to represent concepts and edges to represent relationships between them. Frames. Structured templates for representing objects or situations, defining their attributes and relationships. Ontologies, a formal description of a domain detailing concepts and their relationships, commonly used in AI to model complex domains. Reasoning allows AI to make inferences from existing knowledge. There are different types. Deductive reasoning derives specific conclusions from general rules. For example, if all birds can fly and an eagle is a bird, then an eagle can fly. Inductive reasoning generalizes from specific examples. For instance, if you've seen only white swans, you might assume all swans are white. Abductive reasoning forms hypotheses to explain observations. For example, if the ground is wet, you might infer it has rained recently. First-order logic, or FRL, extends basic propositional logic with quantifiers and variables, allowing more expressive representations such as all humans are mortal. Semantic web, a framework for sharing information in a way AI systems can understand using ontologies for complex data representation. Welcome to this section on cognitive computing. Cognitive computing mimics human thought processes in AI systems, enabling machines to analyze large amounts of unstructured data and make intelligent decisions. Let's explore its core ideas. Cognitive computing is AI that emulates human reasoning and problem-solving by using natural language processing, machine learning, and pattern recognition. Key features include adaptive learning, which is the ability to learn from new information and adjust accordingly. Contextual awareness, which means understanding data in context, for example, identifying the meaning of bank based on context. Interactive systems, which are user-friendly interfaces that enable smooth interaction between humans and AI. Some common techniques in cognitive computing include natural language processing, or NLP, which enables machines to understand and generate human language. For example, voice assistants like Siri and Alexa rely on NLP to process spoken commands. Machine learning allows systems to identify patterns and learn from data without being explicitly programmed. For instance, cognitive systems can recommend products based on customer behavior patterns. Computer vision is another technique where cognitive systems can interpret visual data, enabling them to recognize images, objects, or even emotions in photos. Welcome to this section on Artificial General Intelligence, or AGI. AGI represents the next level of AI, where machines possess the ability to understand, learn, and apply intelligence across a wide range of tasks, just like humans. Let's break it down. AGI refers to AI that can perform any intellectual task that a human being can. Unlike narrow AI, which excels in specific tasks, for example, chess, AGI aims to generalize its intelligence across various domains. Key characteristics include versatility, where AGI can switch between tasks and apply knowledge from one domain to another, much like humans can. Another characteristic is learning and adaptation, meaning AGI can learn new concepts, skills, and ideas without explicit reprogramming. Research in AGI faces several hurdles, including common sense reasoning, as teaching machines to understand everyday human logic is difficult. Another challenge is learning efficiency, where AGI needs to learn with fewer data and experiences than current AI models. Finally, ethical and safety concerns are paramount. Developing AGI responsibly to ensure it benefits humanity without causing harm is crucial. Welcome to this section on multi-agent systems. These systems involve multiple intelligent agents that interact with each other to solve complex problems. Let's explore how they work and their applications. A multi-agent system, or MAS, is a group of AI agents that work together, sometimes competitively, to achieve a goal. Each agent in the system has its own set of goals, perceptions, and actions. Key characteristics include autonomy, where agents can operate independently and make decisions without central control, and collaboration or competition, where agents can cooperate to solve problems or compete in environments with limited resources. The MAS are used in various fields, including robotics, where multiple robots work together to complete tasks like warehouse management, and traffic management, where traffic flow is managed by coordinating vehicles and traffic signals. In game theory, MAS are used in competitive environments to simulate behaviors like negotiation, auctions, or resource allocation. Welcome to this section on automated planning and scheduling. This field enables AI systems to make decisions about the sequence of actions to achieve specific goals efficiently. Let's look at how it works. Planning refers to determining a series of actions needed to reach a goal, while scheduling ensures tasks are performed at the right time, in the correct order. State space, the set of all possible conditions the system can be in. AI must navigate through this space to find the best plan. Goal-based planning AI systems create plans by considering the initial state and the desired outcome. For example, a robot navigating from point A to point B in a factory. Scheduling algorithms. These prioritize tasks based on available resources or deadlines. Think about assigning work shifts for employees or managing production lines. Welcome to this section on artificial life, or a life. A life studies synthetic systems that mimic life processes, enabling the creation of lifelike behaviors in digital environments. Artificial life involves creating simulations or models that replicate biological processes such as evolution, reproduction, and self-repair in artificial environments. Key aspects include evolutionary algorithms. These simulate natural evolution, where systems adapt and optimize over generations. Cellular automata. Simple rules govern how cells or agents evolve over time, resulting in complex behaviors. Robotics. AI principles guide the development of robots that can adapt to changing environments. Computer simulations. Our life models are used to study biological evolution, ecosystems, and population dynamics in virtual environments, for example, simulating predator-prey relationships to study ecological balance.
Welcome to the section on generative AI. In this part of the course, we'll explore how AI can generate new data, whether it's images, text, music, or more. Generative AI has revolutionized many industries and applications, and today we'll dive into its concepts, models, and techniques. Let's start with a basic definition. Generative AI refers to models that can create new content like images, text, or even videos, based on the patterns learned from existing data. This is different from traditional models, which usually focus on tasks like classification or regression. Generative AI is responsible for creating rather than just predicting. Now let's discuss some core concepts of generative models. At the heart of these models is the idea of learning a probability distribution from the data. The model learns the underlying patterns in the training data and then generates new samples that follow the same distribution. A key concept here is the latent space, a lower dimensional representation of the data, where the model captures abstract features that describe the data it's learned. This latent space helps the model generate new data points that are similar but not identical to the original data. Generative models can be grouped into different types. The most common include autoregressive models. These models generate new data step by step, one part at a time. For example, in text generation, The model predicts the next word based on the words that came before it. Examples include RNs and transformers. Variational autoencoders, or VAEs, are a type of generative model that learns to compress data into a latent space and then generate new data from that space. The process involves an encoder that converts data into the latent representation and a decoder that generates data from it. Generative adversarial networks, or GANs, consist of two parts: a generator that creates fake data, and a discriminator that tries to distinguish between real and fake data. The generator gets better over time by learning to fool the discriminator. Diffusion models, a newer approach that generates data by progressively refining noise into coherent data, used in models like DAL-E and Stable Diffusion. Now let's go deeper into variational autoencoders, or VAEs. VAEs are built with two main components, an encoder and a decoder. The encoder compresses input data into a lower dimensional latent space, and the decoder reconstructs the original data from that space. This model works by optimizing two losses: reconstruction loss, which measures how accurately the model reproduces the input, and KL divergence, which ensures that the latent space has a well-defined structure. Moving on to generative adversarial networks, or GANs, which are one of the most exciting developments in generative AI. A GAN has two neural networks competing with each other, a generator and a discriminator. The generator creates fake data, and the discriminator evaluates whether the data is real or fake. Over time, the generator improves, and the data it produces becomes indistinguishable from real data. However, training GANs can be challenging due to issues like mode collapse, where the generator produces limited types of data, and instability in the training process. Various techniques, such as Wasserstein GANs, have been developed to address these challenges. Next, we'll explore transformer-based models for generation, such as GPT. These models are built using self-attention mechanisms and have proven highly effective in generating coherent text. For instance, GPT-3 is capable of generating human-like text given a prompt, thanks to its autoregressive structure that predicts the next word based on previous ones. Now let's discuss some recent advances, starting with diffusion models. These models are gaining attention due to their ability to generate high-quality images by starting with random noise and gradually refining it to produce a coherent image. Models like DAL-E and Stable Diffusion use this approach to create stunning visuals from text prompts. We've also seen breakthroughs in large language models, or LLMs. GPT-3, BERT, and others can generate human-like text, understand context, and answer complex questions. These models have applications in chatbots, content creation, and more. In terms of real-world applications, generative AI is being used in a variety of fields: art and creativity. AI tools like DAL-E and Midjourney help artists create digital artwork by generating images based on text descriptions. Text generation ChatGPT and similar models are used for generating text in applications like customer service bots, content creation, and even creative writing. Music generation AI tools like JukeDeck can create music compositions based on the style and input provided by users. Gaming procedural content generation allows game developers to create large game worlds and complex characters without manual input. Synthetic data generation AI can generate synthetic data, which is useful in scenarios where privacy concerns limit the availability of real-world data. Now, let's take a look at the ethical challenges of generative AI. One major issue is the rise of deepfakes, where AI generates realistic images or videos of people that can be used maliciously. There's also the problem of bias in the generated content, as these models often inherit biases from the training data. Additionally, there are concerns about copyright and ownership of the content generated by AI, especially in creative fields. And finally, the environmental impact of training large generative models is becoming a growing concern, as they require significant computational resources. Finally, evaluating generative models is tricky. Common metrics include the inception score and Frechet inception distance, which are used to measure the quality of generated images. However, subjective evaluation, particularly in text generation, is often necessary to assess the coherence, creativity, and relevance of the generated content. To wrap up, generative AI is a rapidly evolving field with enormous potential, but it also brings technical and ethical challenges.
Yo, what's up everyone? Today we're diving into the world of generative AI. Now I know what you might be thinking, AI? That sounds super complicated, but trust me, it's not as daunting as it seems. We're talking about tools and platforms that are designed for everyone, even if you've never coded a day in your life. That's right, generative AI has opened up a whole new world of possibilities for creativity, productivity, and even just plain fun. We're talking about generating text, images, videos, code, and even automating entire workflows, all with the help of AI. And the best part is a lot of these tools are available through user-friendly platforms, APIs, or even no-code tools, making them super accessible. So whether you're an artist looking for new ways to express yourself, a marketer crafting compelling copy, a developer seeking coding assistance, or just someone curious about the potential of AI, this video is for you. Let's break down the barriers and unlock the power of generative AI together. First up, let's talk text generation. Think about it. AI that can write for you. Sounds crazy, right? But tools like ChatGPT are making it happen. ChatGPT is like having a brainstorming partner on demand. Need help writing a blog post, generating creative content, or even just drafting an email? ChatGPT's got your back, and it doesn't stop there. We've got Jasper, which is specifically designed for crafting marketing copy that converts. Need to write a killer ad or a compelling product description? Jasper's your go-to. And if you're looking to rephrase text or polish up your writing, Quillbot is like a supercharged grammar checker and paraphrasing tool rolled into one. Next up, let's talk about something truly mind-blowing: AI image generation. Remember those sci-fi movies where you could just describe an image and the computer would create it? Well, that's basically what tools like DALL-E 3 are doing right now. You literally type in what you want to see and DALL-E 3 brings it to life. It's like magic. But it's not just about generating random images. Midjourney takes things to a whole new level, allowing you to create stunning artistic visuals that look like they were created by a human artist. And for those of you who need design assets for social media presentations or marketing materials, Canva Magic Media is a game changer, letting you generate custom images directly within Canva. Alright, now let's get into the realm of video and audio. Imagine being able to create professional-looking videos without needing a fancy camera crew or editing software. That's the power of tools like Pictory. You can easily convert text into engaging videos, complete with visuals, music, and more. And if you need an AI avatar to represent you in your videos, Synthesia has got you covered. Create your own AI spokesperson to deliver your message with personality and style. And for those times when you need high-quality text-to-speech, Murph.ai is the answer. It's like having a professional voice actor at your beck and call, ready to narrate your videos, presentations, or even audiobooks. Okay, coders in the house? This one's for you. Imagine having an AI pair programmer that could help you write better code, faster. That's what GitHub Copilot is all about. It integrates right into your coding environment, providing intelligent code suggestions and even generating entire functions based on your comments. And if you're just getting started with coding, or if you need a quick and easy way to build web apps without writing a ton of code, check out Replit Ghostwriter and Bubble. Replit Ghostwriter offers a collaborative coding environment right in your browser, while Bubble empowers you to build fully functional web applications using a visual drag-and-drop interface. Now let's talk about one of the most powerful applications of AI automation. Imagine being able to automate repetitive tasks, streamline your workflows, and free up your time for more important things. That's where tools like Zapier come in. Zapier lets you connect different apps and automate tasks between them without writing a single line of code. And if you want to take your automation to the next level, you can even extend the capabilities of ChatGPT with plugins. These plugins give ChatGPT access to real-time information and allow it to interact with other apps, making it even more powerful. And for those of you who want to build your own chatbots, ManyChat is an excellent platform that makes it easy to create conversational AI experiences. Generative AI isn't just about automating tasks and creating cool stuff. It can also help you be more productive and efficient in your everyday life. Take Notion AI, for example. It integrates with the popular note-taking app Notion and provides features like AI-powered writing assistance, note summarization, and even content generation. And if you're looking to improve your writing skills, Grammarly is a must-have. It goes beyond basic grammar and spelling checks, offering suggestions for clarity, tone, and style. And for those times when you need to conduct research or gather information quickly, Consensus is a powerful AI-powered research tool that can summarize findings from scientific papers and other sources. Finally, let's explore some specialized AI tools that are pushing the boundaries of what's possible. For those of you in the world of 3D modeling, Luma.ai is a game changer. It allows you to create incredibly realistic 3D models from photos and videos, making it easier than ever to bring your ideas to life. And for video editors out there, Runway ML is like having a whole suite of AI-powered video editing tools at your fingertips. From object removal and style transfer to motion tracking and video generation, Runway ML opens up a world of creative possibilities. And for those of you who want to create stunning presentations, Beautiful.ai is an AI-powered presentation design tool that helps you create professional-looking slides with ease. So there you have it, a glimpse into the incredible world of generative AI. As you've seen, these tools are not just for tech wizards and AI experts. They're designed to be accessible to everyone, regardless of your technical skills. Whether you're an artist, a writer, a marketer, a developer, or just someone who wants to explore the potential of AI, there's a tool out there for you. The best way to get started is to simply choose a tool that interests you, sign up, and start experimenting. Most of these platforms offer free trials or free plans, so you can try before you buy. And if you want to dive deeper, there are tons of tutorials, courses, and resources available online. The future of AI is here, and it's more exciting than ever. So, what are you waiting for? Jump in, explore, and unlock the power of generative AI for yourself.
Welcome to the section on prompt engineering. In this session, we'll explore one of the most important skills when working with language models: how to craft effective prompts to get the best results. This is crucial because large language models like GPT-4 rely on the input you provide to generate high-quality, relevant, and accurate responses. Let's dive into what prompt engineering is, why it matters, and strategies you can use to design powerful prompts. To begin, let's answer the question, what is prompt engineering? Prompt engineering is the process of designing and refining the input, or prompt, that you give to a language model in order to get the desired output. Think of the prompt as the instructions or context you provide to guide the AI. By carefully crafting this input, you can significantly improve the quality, relevance, and accuracy of the AI's responses. A well-designed prompt can make the difference between an output that's vague, incorrect, or incomplete, and one that is clear, insightful, and directly answers your needs. Prompt engineering is crucial for several reasons. Maximizing accuracy. The better your prompt, the more accurate and relevant the response. When working with AI, small changes in phrasing can yield dramatically different results. Clarifying ambiguity. AI models can struggle with ambiguous or incomplete prompts. Engineering a prompt that provides enough context and detail helps the model focus on what's important. Customizing outputs. You can tailor outputs to specific tasks, whether it's answering questions, generating creative content, summarizing text, or even coding. Different tasks require different prompt styles. Efficiency. A well-crafted prompt reduces the need for back-and-forth corrections, which saves time when working with AI systems. An effective prompt consists of several key components. Clarity. The prompt should be as clear and concise as possible. Avoid ambiguity. State explicitly what you want the AI to do. Context. Providing context can help the AI understand the purpose of the task. For instance, if you're asking the AI to write a blog post, you might specify the topic, tone, and target audience. Instruction: direct the model with specific instructions. For example, instead of saying explain AI, you could say explain the concept of artificial intelligence in simple terms for a beginner audience. Constraints: if there are limitations on the output, like word count, format, or style, be sure to include those. For example, summarize this article in 100 words. Examples: if you want the AI to follow a certain style or format, providing examples can help. For instance, if you're asking for a recipe, you can give an example recipe first to demonstrate the desired format. Let's now look at strategies to enhance prompt design. Be specific, not general. The more specific your request, the better the response. For example, instead of saying "tell me about climate change," a more specific prompt would be, "Summarize the effects of climate change on polar ice caps and sea levels." Role-playing. One powerful strategy in prompt engineering is assigning a role to the AI. You can instruct it to take on the persona of a specific professional or even a well-known historical figure. This technique helps generate responses that align with specific expertise or styles. For example, you are a software engineer. Explain the concept of recursion in Python, or imagine you are a financial advisor. Provide investment advice for someone with a moderate risk appetite. When assigning the AI a role, it often shifts the tone and complexity of its responses to match the persona you've specified. You can use this to tailor the response to particular fields like law, medicine, or academia. Use of delimiters. If you're working with multi-part prompts, delimiters such as quotation marks or brackets can help define different sections. For example, translate the following sentence from English to French: "The weather is beautiful today." Step-by-step instructions. When tasks are complex, break them down into smaller steps. For example, first, summarize the following article. Then, highlight 3 key points that a high school student would find interesting. Ask for multiple options. Sometimes it helps to ask for more than one answer. For example, give me 3 different ways to introduce a podcast on AI trends. Temperature and length control. When using temperature settings in some systems, you can control the creativity of the response. A higher temperature makes the model more creative, while a lower temperature makes it more deterministic. You can also ask for a specific length. Write a 200-word summary of this research paper. Even though prompt engineering is incredibly powerful, there are a few pitfalls you'll want to avoid. Vagueness. Avoid prompts that are too vague or general. If the prompt is unclear, the model might not know how to respond effectively. Underspecification. Don't assume the AI knows the context or task. Provide as much relevant information as needed for the AI to perform well. Overloading the prompt. While context is important, don't overload the model with too much information. Long or overly complex prompts can confuse the AI. Neglecting examples. If the model struggles to generate a specific style or format, providing examples to guide its response can help. Ignoring iteration. Prompt engineering often involves a process of trial and error. Don't expect perfect results from the first prompt. Iterate and refine to get better outcomes. Prompt engineering is a skill that finds applications across various fields. Content generation. Writers, marketers, and content creators use AI to draft articles, blogs, product descriptions, and social media posts. Crafting the right prompt ensures that the content is engaging and relevant. Role-playing prompts. As discussed earlier, role-playing is a highly practical use case. This strategy is especially useful in professional settings. For example, a medical student could prompt the AI by saying, "You are a medical professional." Explain the symptoms of diabetes in layman's terms. In creative writing, an author might ask, "You are William Shakespeare. Write the opening scene of a modern romantic comedy." By simulating specific expertise, the AI can generate responses in the tone, terminology, and style that would align with the profession or character. Summarization AI can summarize large documents or research papers. Providing detailed instructions ensures concise and accurate summaries. Coding assistance. Engineers can use prompt engineering to request code snippets or get help debugging. For example, write a Python function that reverses a string. Chatbots and virtual assistants. For those building AI-powered chatbots, prompt engineering helps create natural, meaningful interactions. For instance, as a virtual assistant, help the user book a flight and hotel for a business trip. Data querying. In data science, prompts can be used to retrieve insights or analyze trends. You can ask, generate a statistical summary of this dataset focusing on age and income distribution. Education and learning AI models can be used to teach new topics, explain difficult concepts, or quiz students. An effective prompt for this might be, explain the theory of relativity like you are teaching a high school physics class. Iteration is a key part of prompt engineering. Often, the first prompt you create might not yield the best results. So, how do you iterate? Analyze the output. Look carefully at the AI's response. Is it relevant? Is it missing details? Does it match the expected format or style? Refine the prompt. Based on the output, adjust your prompt. Add more context, clarify instructions, or break down complex tasks into smaller ones. Test and repeat. Keep testing different variations of your prompt. Each time you'll get closer to the desired result. This iterative process is key to mastering prompt engineering. As language models evolve, prompt engineering will remain a vital skill. However, we are seeing trends that indicate the future may bring more advanced techniques like automated prompt tuning techniques, where the AI itself learns how to refine and optimize prompts for better outputs. Few-shot and zero-shot learning. As models get better at understanding tasks with minimal examples, the need for explicit prompt engineering may lessen, but it will still play a role in maximizing efficiency. Task-specific AI systems. Future AI systems may become more specialized, requiring less manual prompt design, but expertise will still be needed to guide these models effectively, based on the specific tasks or industries they serve. In conclusion, prompt engineering is an essential skill for anyone working with AI language models. By mastering the ability to craft effective prompts, you can dramatically improve the performance of these models across a wide range of tasks, whether you're generating text, solving problems, or building AI systems. Remember, start simple, iterate on your prompts, and explore the full potential of what these models can do when properly guided. That wraps up our lesson on prompt engineering. Thank you for joining. Yo, what's up everyone? Welcome back. Now, you know I'm all about that tech, and lately, everyone's been asking about the hottest field out there. Artificial intelligence. AI is absolutely blowing up, and for good reason. It's changing the game in everything from healthcare to gaming, and that means massive opportunity. But navigating the world of AI careers can feel like trying to pick a phone with your eyes closed, right? That's why we're breaking down the top 10 AI careers, complete with your very own roadmap to success for each one. Whether you're a coding guru or just starting out, we've got you covered. So stick around and let's unlock your AI potential. First up, we're diving into the world of machine learning engineers. These are the masterminds behind the algorithms and models that let machines learn and make decisions on their own. Think about it, your Netflix recommendations, self-driving cars, even those hyper-realistic filters on social media, that's all powered by machine learning. To conquer this career path, you're going to need a strong foundation in programming. Python or R are your best bets. And listen, I know math isn't everyone's favorite subject, but trust me, you gotta get comfortable with linear algebra, calculus, and statistics. These tools are key to understanding how these complex algorithms actually work. Of course, none of that matters if you don't have data to work with. Data handling is crucial, so learn how to clean, process, and analyze it like a pro using libraries like Pandas and NumPy. Once you've got the basics down, it's time to dive into the world of machine learning algorithms themselves. We're talking supervised learning, unsupervised learning, and even reinforcement learning. The same tech that's teaching AI to play games at superhuman levels. Next up, we're talking about the data detectives, the insight ninjas, the ones who can find a needle in a haystack of information data scientists. These folks live and breathe data, using their skills to find hidden trends and insights that others miss. Just like with machine learning, programming is non-negotiable here. Python or R are your go-to languages. But data science is about more than just code. You need a deep understanding of data analysis techniques. Think Pandas, NumPy, and Matplotlib. These are your weapons of choice. Of course, you can't forget about statistics. Descriptive, inferential, hypothesis testing, you need all of it in your arsenal. Now, here's the thing about insights. They don't mean much if you can't communicate them effectively. That's where data visualization comes in. Master tools like Tableau, Power BI, or even Matplotlib and Seaborn to tell compelling stories with your data. Finally, to really level up your data science game, you gotta understand machine learning algorithms. Regression, classification, clustering, these are your keys to unlocking predictive power and taking your analysis to the next level. Alright, for those of you who want to live on the cutting edge, who dream of making groundbreaking discoveries in AI, this one's for you, the AI research scientist. These are the pioneers, the trailblazers who are pushing the boundaries of what AI can do. But listen, this path is not for the faint of heart. It demands a deep dive into the theoretical foundations of AI, and that means getting comfortable with some serious math. We're talking advanced linear algebra, calculus, probability, statistics, the works. And of course, you'll need to master programming languages like Python, Julia, or MATLAB, the tools of the trade in AI research. But here's the thing about research. It's not just about crunching numbers and writing code. You need to be able to dive deep into academic papers, understand the latest breakthroughs, and even contribute your own research to the field. That means publishing your work in top AI conferences like NeuraPS, CVPR, or ICML. It's a challenging path, but for those who are passionate about advancing the field of AI, it's incredibly rewarding. Now, let's talk about a field that's all about understanding the most complex and nuanced form of data out there: human language. That's right, we're diving into the world of natural language processing, or NLP, and the engineers who make it all happen. These are the people who are building the chatbots, the translation systems, the sentiment analysis tools that are changing the way we interact with technology. If you're ready to decode the language of AI, you gotta start with a strong foundation in programming, specifically Python and NLP libraries like NLTK, Spacey, and Hugging Face's transformers. But coding is just the beginning. To truly understand language, you need to think like a linguist. That means getting a handle on syntax, semantics, phonetics, all the building blocks of language. Once you've got that down, it's time to explore the world of NLP techniques. Tokenization, lemmatization, POS tagging, named entity recognition. These are your tools for dissecting and understanding text. And of course, we can't forget about deep learning. Transformer models like BERT and GPT are revolutionizing NLP, and you need to know how to fine-tune them for specific tasks like sentiment analysis, summarization, and text classification. With great power comes great responsibility, right? That's where AI ethics specialists come in. These folks are the guardians of responsible AI, making sure this technology is developed and used in a way that benefits humanity. Now you might be thinking, ethics in tech? What? But listen, it's more important than ever. We're talking about bias in algorithms, data privacy concerns, the potential impact of AI on jobs. These are big issues, and AI ethics specialists are on the front lines. To navigate this space, you need a solid understanding of core AI concepts and machine learning algorithms, but you also need to be well-versed in the ethical implications of this technology. That means studying AI ethics principles, data privacy laws like GDPR, and understanding how bias can creep into AI systems. But it's not just about identifying problems, it's about finding solutions. That's why AI ethics specialists need to be skilled in risk management, policy analysis, and collaboration. You'll be working with legal teams, technical teams, and everyone in between to make sure AI is used for good. Alright, who here dreamed of building their own robots as a kid? Well, guess what? That dream can be your reality as an AI robotics engineer. These are the masterminds behind those intelligent machines we used to only see in sci-fi movies. But this isn't just about bolting metal together. We're talking about robots that can learn, adapt, and interact with the world in increasingly sophisticated ways. To break into this field, you need a solid foundation in programming, specifically C++ and Python. And trust me, a strong understanding of robotics fundamentals is non-negotiable. We're talking kinematics, dynamics, control theory, the stuff that makes robots move and groove. But here's where it gets really interesting. AI. You'll be using cutting-edge techniques like computer vision, deep reinforcement learning, and more to give your robots that extra dose of intelligence. Oh, and don't forget about the Robot Operating System, or ROS. It's the backbone of many robotic systems, and you'll need to know your way around it. And of course, simulation tools like Gazebo and MATLAB are your best friends for testing and refining your robotic creations in a virtual world before you unleash them on the real one. Now let's talk about giving machines the gift of sight. And no, I'm not talking about some sci-fi movie magic. I'm talking about computer vision, a field that's all about teaching computers to see and interpret the world through images and videos. This is the tech that's powering everything from self-driving cars to facial recognition systems, and it all starts with computer vision engineers. To join the ranks of these digital visionaries, you'll need a strong foundation in mathematics, especially image processing fundamentals, linear algebra, and calculus. And of course, programming is a must. Python, along with libraries like OpenCV, will be your go-to tools for image manipulation and analysis. But here's where things get really interesting. Deep learning. Convolutional neural networks, or CNNs, are the powerhouses behind many computer vision tasks. You'll need to understand how they work, how to train them, and how to use them for tasks like object detection. Think YOLO and RCNN image segmentation, and even image generation using GANs. But computer vision isn't just about two-dimensional images anymore. Three-dimensional vision is where it's at. You'll want to explore depth estimation, three-dimensional reconstruction, and even simultaneous localization and mapping, which helps robots navigate the world autonomously. We've talked about the tech wizards, the data gurus, the robot whisperers, but what about the people who bring it all together? That's where AI product managers come in. These are the folks who bridge the gap between the brilliant minds building AI and the real-world problems it can solve. Now you might be thinking, product manager, that doesn't sound very AI, but trust me, it's all connected. AI product managers need a deep understanding of AI fundamentals, but they also need that business savvy to identify opportunities where AI can make a real impact. Think of them as the conductors of an orchestra, bringing together engineers, data scientists, designers, and everyone in between to create amazing AI-powered products. But it's not just about having a vision, it's about execution. AI product managers need to be masters of product management skills like roadmap creation, user story writing, and prioritization. They need to understand how to translate business needs into technical requirements, and guide the development process from start to finish. And here's the thing. AI is constantly evolving, which means AI product managers need to be agile and adaptable. They need to stay up to date on the latest advancements in AI and be ready to pivot their strategies as needed. Alright, let's talk about the AI troubleshooters. The ones who swoop in with solutions when businesses are facing AI-related challenges. That's right. We're talking about AI consultants. These folks are the AI equivalent of special ops, ready to deploy their expertise wherever it's needed. Now, you might be thinking, consultant, is that just a fancy word for advisor? And yeah, there's definitely an element of that. But AI consultants are more than just advisors, they're doers. They roll up their sleeves, dive into the data, and work closely with businesses to design and implement custom AI solutions. But here's the catch. AI consultants need to be fluent in two languages, the language of tech and the language of business. On the one hand, they need to stay up to date on the latest AI technologies, tools, and frameworks. They need to know their CNNs from their RNNs, their TensorFlow from their PyTorch. But on the other hand, they need that business acumen to understand how AI can solve real-world problems and create tangible value. It's about bridging that gap, communicating complex AI concepts to non-technical stakeholders, and guiding businesses through the often daunting process of AI adoption. It's a challenging role, but for those who love solving problems and seeing the impact of their work firsthand, it's incredibly rewarding. We've talked about building AI models, training them, even deploying them, but what happens after you hit that deploy button? Who keeps those AI systems running smoothly, making sure they're performing at their best? That's where AI operations engineers, or MLOps, DevOps engineers come in. These folks are the unsung heroes of the AI world, ensuring that those AI-powered applications we all rely on are always up and running. Now you might be thinking, operations? That doesn't sound very glamorous, but listen, in the world of AI, reliability is everything. Imagine your favorite AI-powered app constantly crashing, or worse, delivering inaccurate results. Not a good look, right? That's why AI operations engineers are so crucial. They're the ones who build and maintain the infrastructure that keeps AI systems running like well-oiled machines. They're masters of cloud platforms like AWS, Azure, and GCP. They live and breathe CI/CD pipelines, ensuring that code changes are deployed smoothly and efficiently. And they're experts in containerization technologies like Docker and Kubernetes, making sure those AI models are packaged and deployed in a way that's scalable and reliable. But it's not just about keeping the lights on. AI operations engineers are also responsible for monitoring model performance, identifying and troubleshooting issues, and implementing version control to keep track of all those model iterations. They're the guardians of AI uptime, and trust me, that's a job that deserves some serious respect. So there you have it, folks. Those are just 10 of the incredible career paths waiting for you in the exciting world of AI. Whether you're passionate about building intelligent machines, analyzing mountains of data, or shaping the ethical future of AI, there's a place for you in this rapidly growing field. Remember, this is just a starting point. The world of AI is constantly evolving, so stay curious, never stop learning, and who knows what amazing opportunities you'll unlock.
Yo, what's up everyone? Welcome back. Now you know everyone's been talking about AI lately. It's literally changing the game in every industry. But here's the thing. You don't need to be a coding wizard to land a sweet gig in the AI world. That's right, even if you haven't mastered Python or built your own neural network from scratch, there's a whole world of AI careers out there ready for you. So, if you're ready to ditch the coding bootcamp and still ride the AI wave, you've come to the right place. In this video, we're diving deep into 10 exciting AI careers that don't require you to be a coding ninja. We're talking about roles where your creativity, problem-solving skills, and business acumen can really shine. Let's get started. First up, we have the AI Product Manager. Think of this role as the conductor of the AI orchestra. You're the one bringing together the technical geniuses building the AI with the business minds who know how to sell it. You'll be deep in the AI product lifecycle, from that initial spark of an idea all the way to getting it out into the world. You'll be juggling market research, user needs, and those ever-evolving AI capabilities to create products that are both innovative and user-friendly. It's a fast-paced role that requires a strategic mind, a knack for communication, and a deep understanding of both the tech and the business side of things. Next, let's talk about the AI consultant. Now, if you're someone who loves diving into problems and finding those elegant AI-powered solutions, this might be the perfect role for you. As an AI consultant, you're the go-to expert for businesses looking to leverage the power of AI. You'll be analyzing their operations, identifying areas where AI can make a real impact, and recommending the right AI strategies to boost efficiency, automate processes, and gain a competitive edge. The best part? You don't need to be knee-deep in code. Your focus is on the big picture, understanding the potential of AI and how it can be applied to solve real-world business challenges. Now let's talk about the unsung heroes of the AI world, the AI trainers and data annotators. These folks are the ones who make sure the AI is actually learning something useful. Imagine you're teaching a kid how to identify different fruits. You wouldn't just show them a blurry picture and say, "Figure it out." You'd show them clear examples, label them, and correct their mistakes. That's what an AI trainer does, but for AI models. They work with massive datasets, cleaning them up, labeling images, transcribing audio. Basically, they're making sure the data used to train AI systems is top-notch. It's detail-oriented work, but it's absolutely crucial for building accurate and unbiased AI. AI ethicist, the guardian of responsible AI. Now, as AI becomes more powerful, we need to make sure it's being used responsibly. And that's where AI ethicists come in. They're like the ethical compass guiding the development and deployment of AI technologies. AI ethicists grapple with the big questions, things like bias in algorithms, data privacy, and the potential impact of AI on society. They work to ensure that AI is developed and used in a way that benefits everyone, not just a select few. It's a role that requires a strong moral compass, a deep understanding of ethical principles, and the ability to advocate for responsible AI practices within organizations. AI Project Manager, the AI Orchestrator. Next up, we have the AI Project Manager. If you're someone who thrives in a fast-paced environment, loves coordinating teams, and gets a kick out of bringing AI projects to life, this could be your calling. Just like any project manager, you'll be in charge of timelines, budgets, and making sure everyone's on track. But here's the twist. You're dealing with the unique challenges of AI projects. You'll be bridging the gap between the technical teams building the AI and the business stakeholders who need to see results. It's about having a solid understanding of the AI development process, managing expectations, and ensuring those AI projects are delivered on time and within budget. AI UX UI Designer crafting seamless AI experiences. Let's face it, even the most powerful AI is useless if people can't figure out how to use it. That's where our AI UX UI designers come in. They're the ones making AI apps and systems intuitive, user-friendly, and even enjoyable to use. They're thinking about how humans interact with AI, designing interfaces that are easy to understand and navigate. It's about making those complex AI features feel seamless and natural, so users can focus on what really matters, getting things done. If you have a knack for design, a passion for user experience, and an interest in how people interact with technology, this could be the perfect AI niche for you. Now, let's talk about the folks who bring AI to the masses. The AI sales specialists. These are the ones on the front lines, spreading the word about the power of AI and connecting businesses with the right AI solutions. It's a role that requires a deep understanding of AI technologies, the ability to translate those technical features into tangible business benefits, and the sales skills to close deals. You'll be meeting with potential clients, understanding their pain points, and showing them how AI can help them overcome challenges, optimize their operations, and achieve their goals. Next, let's give a shout out to the AI technical writers. They're the ones taking those complex AI concepts and translating them into clear, concise, and user-friendly documentation. We're talking about everything from technical manuals and white papers to those helpful tutorials that guide users through AI software. They're making AI accessible to everyone, whether you're a tech-savvy developer or a business user just getting started with AI. It's a role that requires a passion for writing, a knack for explaining complex topics in a simple way, and a solid understanding of AI technologies. Now, let's talk about the AI business analyst. They're like detectives, but instead of solving crimes, they're solving business problems with the power of AI. They work at the intersection of business and technology, using their analytical skills to identify areas where AI can make a real impact. They're digging into data, understanding business processes, and collaborating with both AI and data teams to develop those AI-driven solutions. It's a role that requires a unique blend of business acumen, data analysis skills, and an understanding of AI capabilities. Finally, let's talk about the AI marketing specialist. In today's data-driven world, marketing is all about personalization, targeting the right audience with the right message at the right time. And that's where AI comes in. AI marketing specialists use AI tools and technologies to take their marketing campaigns to the next level. They're analyzing consumer behavior, predicting trends, and using AI to personalize customer experiences. It's a role that requires a mix of marketing expertise, data analysis skills, and a deep understanding of how AI can be used to optimize marketing campaigns and drive results. So there you have it, 10 incredible AI careers that don't require you to be a coding superstar. As you can see, the AI field is vast, and there's a place for everyone, regardless of your technical background. The key is to find a role that aligns with your passions and skills. Do you love solving problems, designing intuitive interfaces, or maybe crafting compelling narratives? There's an AI career path out there for you. Thanks for tuning in, and remember, the future of AI is waiting to be shaped, and you don't need to be a coder to be a part of it. Until next time.